Hello, investment community. My name is Scott Andrews and my company is Titan Labs. We make a device called a street camera. A street camera captures optical events, pulses of light, changes in wavelength, that sort of thing that happen in unimaginably short periods of time, nano, pico, and femtoseconds. So to give you a feeling for it, 1 femtosecond is to a second the same as 1 minute is the lifetime of the universe. So it's a really short period of time we're trying to capture. My company has been focused on not just getting the best specs, which I'm going to talk about in a moment, but also getting a device that's practical and usable. Say you're looking out at the stars and you see a flash of blue light in a supernova. You want to create that down here on Earth in a laboratory like we have in NIF or JLF in Jupiter Laser Facility and in Livermore, or at SLAC in the accelerators or some of their laser facilities. So we want to look at that event that happened out in space in a little, cell in a laboratory, and so we bring in a really intense laser and we hit a metal foil or a puff of gas and we watch what happens. And it's the watching what happens where you need a street camera. You can see when wavelengths of light are shifted, when things go through a different transition from one state to another. And it turns out that more and more interesting stuff happens the faster and faster you're able to look at that phenomenon. And so up till now, most cameras that operated a picosecond or more as their time resolution is the minimum spot that they could resolve, the minimum pulse of light or the minimum change in intensity. Hamamatsu recently came out with a 100 femtosecond street camera, but the problem with it is that there's a 10 picosecond window and 40 seconds of jitter. So you have a 1 in 4 chance of potentially not capturing the event. With my system, based on existing tubes, modeling that we've done, and scientific literature, we believe that we can create 100 femtosecond resolution and a 90 picosecond window. So that's a much bigger window, much bigger target, much bigger batch of temporal data that you have, and then only 15 picoseconds of jitter. So 90 picosecond window, 15 picoseconds of jitter, 100 femtosecond resolution. That's a game changer. That makes it a practical instrument that you can use in the lab, you can use to regulate your fusion reaction, you can use for just about anything. Okay, so you're saying to yourself, you got this great whiz-bang thing that captures femtoseconds of light. Who's going to buy it? The two biggest fusion lasers in the U.S., NIF and LLE, the Laboratory for Laser Energetics in Rochester, are both adding picosecond lasers. It's 1,000 femtosecond lasers, thereabouts, to aid in their fusion reaction. And they're going to need street cameras. There's several picosecond or femtosecond lasers going in Europe. And if you have a femtosecond laser, you need a femtosecond street camera. There's 17 national labs in the U.S., 47 user facilities, hundreds of university laboratories, all of them potential markets for the street camera. There's also many universities over in universities and laboratory facilities in Europe run by CERN. They have the Large Hadron Collider. They have Polytech in France. So where's the business model? Street cameras cost around $110,000 to build for this Perseus. That includes labor, materials. Selling price will be about $200 plus or minus. So it's about a 50% margin, and that 50% is $100,000. That's you don't have to sell too many of those to get up to $1 million or $2 million. It's a lucrative market that's growing. The scientists always want to go shorter, faster, learn more information. They want to push the edges of science, and that's what we want to help them do. Now, if you haven't gotten bored by my rattling on about street cameras and puffs of blue light out in the sky, you can stick around and watch my demo video on the system that I built for Lully Labs in France. It's a 10 picosecond system in which the center camera body was an existing camera, but we built everything in front and in back, and the electronics. We did the shutter, the microchannel plate, the optics, the control systems, everything you see there in the videos. And then also you can learn about my master trigger system, where each sweep speed the camera automatically changes the internal delay for you. It saves a lot of time and increases the chance of getting data on every shot. And then also the front end, where you have a index multiple slit slider with the slit widths labeled, and lots of mounting holes for putting your hardware, your spectrometer, mating, your fiber arrays, whatnot. All right. Talk to you later. Bye. What we have here is the Titan Labs i675TL S20. It is a Imicon 675 camera body, but everything else is custom made and designed by me and built by our company, Titan Labs. So I'm just going to kind of walk you through the camera from the slit through to the CCD. So what we have here is a indexed multiple slit slider. We also have the ability to translate it vertically and horizontally, so if somebody were to burn your microchannel plate or your cathode by putting a high intensity laser, you could translate off of that. We have a micrometer that allows for a precise setting of the focus and be able to record it and go back to for whatever lens. Relays the image from the slit to the photocathode, and in between we have the hidden shutter that's inside this plate here. It sits in about that much space. The power comes out here, and that provides, if you have your focus mode, it'll time out and close after you take a shot. It's just a really nice thing to have, a electronically controlled shutter. And then this is the camera body. On the other side are all the control knobs with the sensor to pick up the position of the sweep settings. On the back end here, this is original, but everything behind it is not. This was designed so you can see here are the springs and are pushing in on the microchannel plate, which makes contact with the phosphor on the end of the tube. And then we transition through a bellows to another lens, same 1.1, 0.4 Nocton lens, and then a Hamamatsu CCD. And this is all with these tied together, these slides very nicely. We have the ability to roll the CCD in the yaw axis, so that when you have your sweep, you're able to align the rows of pixels on the CCD with the sweep, just by simply turning the knob on the goniometer here that rocks it back and forth. We also have the ability to fine-tune focus with a stage here, and it's all captured. That's kind of it. What we have is, on a conventional street camera, you have a continuously variable slit with a big, it's hard to get to the slit and manipulate it. On this one we have the sliding slit, and you can see my assistant leash moving it back and forth to different, each one is indexed so it always comes to the same spot. And if you move it to the middle, go ahead and move it to the middle leash. There you go, one more.
Nope, there we go.
Right there, okay. Now we're in the middle, the normal 100 micron slit that is the most often used. And you can see that you have a wide channel there, and you can put in a variety of masks in order to set up the camera. Okay, so now we've got it set to the middle slit, the 100 microns, and we're going to try to check spatial resolution here, or if we were setting up the camera, we'd want to check that we're in focus and how much active area we have on the cathode. So we have here a slit that's 20 micron slits, or a mask that's got 20 micron slits every 2 millimeters, and you insert that and you can use it to first check your spatial resolution, set your focus, and then also you can see how much active area of the cathode you're getting with the slit every 2 millimeters. So now you can see it's right at the surface of the mask is right at the same plane as the slit. So when you set focus, you'll be doing it right at the image plane. So now we'll move on to a Ronchi ruling target. When you want to fine tweak your spatial resolution, your front end focus, your back end focus, your static focus on the tube, you'll want to use a Ronchi ruling target, and they come in these masks that are 1 inch by 3 inch that are designed to fit in here. We'll make sure the metallic surface is facing that looks good, facing the slit. So now you might have to loosen that. There you go. So it slides in there, and then you can see the window where all the little lower. There you go. Where all the resolution lines are is right on top of the slit, and you just tighten the set screws, and it's firmly in place there, and you can set your spatial resolution on the camera. You can also remove this slit assembly altogether and look at a wider area, or put it when you're initially setting it up. So now when you're operating the camera, you want to make sure you don't get too much light in there, you don't damage it. You want to put an ND, or also you can put a diffuser in the same space, a 2 inch by 2 inch square diffuser. And so we have a little pocket cut out of the front, and that's ND will fit right in the pocket there. And then there's a couple of, once it's in there, there's a couple of clips that hold it in place, and you've got your ND or your diffuser or whatever it is you need for the situation you're in. There's also a series of tapped, in this case M6 holes and M4 holes that you can use for putting whatever custom piece of equipment you want to put on there. You have a fiber array, you have the output from a spectrometer, whatever you need to mate up. We have lots of options in OpenSpace to do it. Okay, so we're going to demonstrate the master trigger functionality that resets your internal delay for each shot. So it automatically sets it so you always have the laser on the screen. So right now we're in 2.9 ns per millimeter. So that's about 50 ns in the system, a little more, 75. Anyway, so we're going to change. So right now it's sensing the position of each one of these knobs that control the sweep speeds. So I'm going to change the sweep speed from 2.9 that it is now down to 1.9. Okay, now it's 1.9, it sensed that. No? Yeah, go ahead and take a shot, Todd. And it's gone. So I'm going to hit the update button, and it'll recalculate the internal delays. And it'll give us in just a second here a new setting. It's done it, so now go ahead and take the shot again. And there's our laser back. It's kind of weak this time. We can turn up the microchannel plate just for fun. Go ahead and shoot it again, Todd. You see, it got much brighter with more gain on the microchannel plate. Okay, go ahead, Todd. There it is. I'm gonna cheat us over a little bit. I have a little bit of a fudge number here. We're gonna just take that and lessen it just a bit. We'll update that.
Shoot it.
Let it update. Okay, go ahead. We'll do that. We'll go ahead and go to 0 on this. Okay, go. Let me update. Okay, go ahead. You can see you're starting to see a little bit of the spatial extent of the laser and the faster scan speed. That's the dispersion and whatnot through the fiber. We've got one more scan speed. We'll go ahead and go there, but then we'll be done. Alright. This one might be so close. You go ahead and get it without updating. Oh, no, we need to update. Alright, go ahead and try it. There she is. So what we were able to do there is go from 200 ns scan speed down to less than a nanosecond scan speed. We had to tweak our fudge factor a little bit, but pretty much we had the spot there for every shot as long as we hit the update button, and save you tons of time in the lab not having to fiddle with changing your laser delay for each shot. So there you go. There it is.
Alright, who wants beverages? We've got some ice water.
We put this in an item.